Welcome to International Conference on Communications, Signal Processing, and their applications. My name is Kabir Nasiru Aliyu, graduate student from Electrical Engineering, King Fahd University of Petroleum and Minerals. I'm here to present direction of arrival estimation in wireless seismic survey using deep learning. Here are the outlines: introduction, literature review, system model, simulation and result, conclusion. Introduction. This research work is divided into three: seismic acquisition, machine learning, and direction of arrival estimation. Seismic acquisition. When we say a seismic acquisition, it's divided into two. We have a cable-based seismic acquisition and we have a wireless seismic acquisition. In cable-based seismic acquisition, seismic signal is generated in pre-localized place. This signal will propagate into the across and then reflected back, and then measured by a geophone sensor. The measured signal will be transferred through a cable into a storage and processing unit. So in wireless seismic acquisition, when the geophone sensors measure the signal, it will transfer the data to a storage and processing unit wirelessly. Why do we need wireless seismic acquisition? The main reason is the drawback in cable base, because it costs about 50% of the operation cost, which is a cabling, and it weighs about 75% of the total weight of the equipment. Another is the advantage of the wireless seismic acquisition, which is the flexibility and high scalability, high productivity, and improvement in the safety and the reduce in the risk of injury. Direction of arrival estimation. It's a process of estimating the direction of the received signal. There are different techniques for estimating the direction of the received signal. One is the beamforming, curve-on, music, esprit, and machine learning. Why direction of arrival estimation in seismic acquisition? Is the localization of the geophone sensors and also improvement in the communication through beam steering for avoidance of interference and increased signal level. Machine learning is an artificial algorithm that is used to learn based on a given example so that it can predict a feature. There are different types of machine learning. We have feed-forward neural network, we have recurrent neural network. Based on the learning techniques, we have supervised learning techniques, unsupervised learning techniques, and reinforcement learning techniques. Why neural network for direction of arrival estimation? One is the real-time response, less competition in execution tasks, and high resolution in prediction. Literature review. So in this research work, we have to carry out two literature review. One is based on the wireless seismic acquisition, and the second is based on the neural network. So based on the wireless seismic acquisition, based on the literature review carried out, we have different architecture. We have stratigraphy, we have subnetwork system, we have two-level subnetwork and three-level subnetwork. So in our research work, we adopt three-level subnetwork, whereby wireless geophone will communicate with the cluster head, and then cluster head will communicate with the wireless gateway node. So in direction of arrival estimation, we consider the algorithm used and the source for the transmission of the signal, and the number of arrays at the receiving end, the search range, and also the resolution. So in our case, we consider one source one source and also 5 arrays at the receiving end. The search range is from -60 to 61 degree resolution. System model. For a system model, firstly we have to distribute the nodes. As you can see here, the blue asterisk is a wireless gateway node, while the red triangle is a cluster head and the dot is a wireless geophone. So the area of the acquisition is divided into cellular network. So we consider a cellular network, whereby here is a single cell which is divided into 3 sectors. Each sector has a uniform linear array antenna for receiving the signal from the geophones. Receive signal formulation. Let's consider a case source transmitting signal to a certain number of arrays. So the channel response is the product of the steering matrix and the complex gain, while the received signal is the product of the channel matrix and the transmitted signal plus the noise. covariance matrix formulation. The covariance matrix is the mathematical expectation of the product of the received signal and its transpose. This gives the covariance matrix which has the diagonal line as the real numbers, while the upper and lower triangular part are the same and complex conjugate. So the lower triangular part and the diagonal line are used to form a single column vector, which is used as an input to the neural network. Simulation and result. Here are the parameters used for generating the training data, while here are the parameters used in the network. We consider different hidden layers, different neurons per hidden layer. The training algorithm is the Lombard Markov. Here are the percentage of the training and the validation set. The scenario used for SNR, we have 0 dB constant, 30 dB constant, 5-step increase, and 1-step linear increase for generating the training data. Here are the performance metric used. We use the root mean square error and the probability of correct estimation. So we consider anything less than 0.5 as a correct estimation. After we train the network, then we evaluate its performance. The legend denotes the SNR used for training the network, while the x-axis denotes the SNR used for testing the network. As you can see here, when we train the network with 0 dB constant, it has a less error at 0 dB. Then when we testing it with linear increase, then the error increase. When we test the network, when we train the network with linear increase of 1 step, then as you can see, it has a good performance. So we fix our network to be trained with 1 step linear increase. Then we evaluate the network with different number of neurons per hidden layer. As you can see here, the network with 30 neurons per hidden layer has a better performance. So we fix our network with the 1-step linear increase and 30 neurons per hidden layer. So here we evaluate the number of hidden layers that we will use in our network. So as you can see here, the network trained with 3 hidden layers has a better performance. So in our model, we choose training data use 1 linear increase, 1-step linear increase, and the number of neurons per hidden layer is 30 neurons. And also the number of hidden layers that we will use is 3 hidden layers. So this network is used in our localization, in seismic acquisition. In conclusion, in our paper, we simulate 3 level wireless seismic acquisition, and also the wireless seismic survey model was divided into hexagonal cell, and each cell is divided into 3 sectors. Directional variable estimation based on deep learning algorithm was considered, and the performance of the network, that is the neural network, was evaluated using 3 network parameters. The neural network that performed the best was selected to be applied in the one sector of the seismic model between the jaw phone and the cluster head, which produced reasonable, highly accurate results. In the future, the directional variable estimation could be utilized for jaw phone localization, which essentially for interpreting the seismic data. Here are the references used for this research. Thank you for listening. For a comment, you can contact this email given below.